First of all, I'd like to say that this is a very special moment for me, because this is the first invited talk I ever got, so I'm very thankful for that. So thanks a lot, organizers. So my presentation is not focused as much on one particular paper or work, but rather on different aspects of quantum information processing in various aspects of quantum causal structures. Yes, but now I have the same problem like Veronica, that it zooms too far in. Yeah, I think I can make it work. So in all the talks, we already had various aspects of like process matrices and indefinite causal structure, but nobody really just defined the basic aspects of what it actually is. So by causal structure, we mean a formalization of cause and effect relations. And if we add quantum superpositions to the mix, we can get quantum causal structures. And one could, for example, imagine that quantum uncertainties blur the light cones of relativity, or that cause and effect relations get put into superposition. And a typical model for that would be the quantum switch that we already encountered several times. And the basic description of that with process matrices has a very simple idea. So we choose some instruments for agents in local labs who are embedded in an environment which may be causally indefinite. And then the process matrix describes the outcome probabilities for the quantum instruments of the agents. And this can be represented just by having the trace, so the Hilbert-Schmidt inner product, of this process matrix W contracted with the Scheu operators of the instruments of the agents. And the Scheu operators are just a way to represent quantum instruments as positive semi-definite operators. And one tries to be as general as possible here. So essentially everything that gives valid probabilities is an allowed process matrix. So first I want to talk about a recent letter format paper by me, Philippe Alagarin, Thomas Zauner, who was a master student of Časlav at that time, and Časlav himself, which would be about quantum teleportation. So why would we need quantum teleportation for processes? Well, the usual notion of having like agents in laboratories implementing any arbitrary instrument might be asked too much for the causal structures that might appear in nature, in particular in quantum gravity scenarios. Like it might be too fragile to implement any instrument, and also actual agents might be far away. So is there a way to teleport the causal structure to laboratories that we have under good control? And a naive physical intuition would say that we need to teleport essentially all the physics over, like everything that participates. But one thing that we already see in the process matrix picture is that it's actually enough to just teleport inputs and outputs. And ideally, this would look like in the figure. So we essentially teleport the inputs out and then teleport the outputs in. And for indefinite causal structures, it cannot really work like this because we have two-way teleportation, and because of this, also two-way classical communication. So this would require that the agents implement the instruments while their sockets in the causal structure, so the blue parts, are active. So in other words, the agents already need to be in the same causal structure that we want to teleport, which isn't very helpful. But it's not a problem for all scenarios that one might encounter. For example, in a quantum comp, which would be just a definite order of agents, one could just put the agents into the right order. Now, a trivial idea how to get around the classical signaling is to simply use post-selection. So if one post-selects all outcomes, then one doesn't need classical communication. But of course, this will have very low success probability. So can one do better than this naive post-selection? And yes, one can. So the basic idea is that one only needs to post-select one of the classical signaling and can actually have the other one if one simply puts the outside agents either in the global past or in the global future. And now we need to verify two very important things. One is that the teleportation actually gives the right statistics. And to do this, one can apply something that's very important to get used with if one works in the field, which would be these category theory style proofs, which means one pushes boxes along wires. So essentially, we can push the yellow agents down into the blue boxes. And then everything is in one lab, and there we know that teleportation works. And while this works mathematically very well, I want to say this is physically highly non-trivial, because the agents are assumed to be in an ordinary flat causal structure, while the probes in the inside, the blue boxes, are in a very exotic causal structure. But nonetheless, this pushing boxes along wires works, and one can formalize this via the so-called link product if one wants to write down equations. So that way, that way one can see that teleportation really gives the right statistics. And there's another subtlety. In principle, the probes or the outside agents could cheat and implement another operation. But still, we want to get no physical inconsistencies. So one has to verify that this scenario, which does have signaling between the outside and the inside, doesn't lead to logical inconsistencies, or in other words, gives a valid process. And we did that, so everything is fine. But yeah, one really has to check that, and it's easy to miss that if teleportation gives everything one thinks one needs. Oopsie. Okay, then next I want to talk about a paper by Philippe Allaguerre, me, Costantino Butroni, and Chaslav again, where we looked at parallel protocols with process matrices. So here we have two process matrices, which simply are causally definite and have signaling in different direction. And now we have two agents, A and B, that have access to both processes. And if one follows the lines through the agent's labs, one will see a causal loop, where each time one has taken the loop, we apply a Pauli X operation, which switches the classical value. And that's inconsistent. That's essentially the process matrix version of the grandfather paradox, what we have here. So it was already known before that the tensor product of process matrices can fail to be a process matrix. And we asked whether there can be a universal replacement. So the first thing that needs to be made clear is we consider fused labs here, like here in the picture, where Bob here in the front has like X on both the process W and W prime. So if everything is completely factorizing and the processes in no way, not even with the agents, never see each other, then there's no problem. So we need to have these fused agents. Or in other words, we want to consider protocols with process matrices that actually take advantage of the fact that we have parallel processes. So this is very common in quantum information for definite causal structures. Like, it's very common that we have like larger states and multiple copies of a channel, and then the large state gets put inside, and in the end there's like one big measurement. For example, if one does quantum Shannon theory and wants to denoise channels, then one would have a scheme like that, where one does something collective with parallel channels. Then we formulated three postulates that we want to have. The first postulate would be bilinearity. So we denote our replacement for the tensor product with a bilinear function mu. So it's will be linear, I should say. And the reason for this postulate is that the process matrix picture uses the interpretation that statistical mixtures of experiments are represented by convex linear functions. So statistical mixtures of experiments means something like in this figure here, that one pushes a button on a machine, and then internally a random number generator is activated that doesn't reveal its result. But the result chooses which, in our case, process matrix gets implemented. So it's now a standard trick in quantum information theory and also general probabilistic theories to extend this convex linearity to full linearity. That's also the reason why CPTP maps that we are considering in usual quantum information are in fact linear and not just convex linear. And we have adapted this construction to bilinear functions. And what is very important is that the extension that one constructs that way is actually consistent with the other postulates that I will now present. The second postulate is that of valid processes. That's precisely what the tensor product got wrong. So how we formulated it in the paper was that we want a valid process matrix whenever the individual process matrices are valid. And now one might critique that that's not a good requirement, that it's far too strong, because most processes are believed to be unphysical, so why should we care? And we failed to point this out in the paper itself, except for the conclusions, and I'm giving here some quotes from the conclusions now. This is much stronger than what we need. What we are really considering in the proof is essentially just processes with definite signaling order, but often these signaling orders are opposite to each other. So essentially it's saying that something like this, the grandfather paradox, will always lead to problems, like no matter what composition rules we are considering. This is what it's saying. And if you want to look in the paper and see really that we are essentially always considering definite signaling direction, just keep the lookout for the set PTI AB that we are defining there. And the third product is, the first postulate is that, of course, we want to get the tensor product back if we have the same definite causal order. And then what we found is that these three postulates are impossible to satisfy simultaneously. And the consequence we saw in that is that we cannot apply the usual asymptotic limit of quantum information theory to process matrices. So this would probably not be a way to do some kind of Shannon theory on process matrices, because we don't have this asymptotic limit. Then in the abstract, I promised to talk about a certain paper, but Veronica already did it, so that's good, because it means I have more time to talk about new things. And this is a running project right now that we are working on. So me and a PhD student called Isaac D. Smith, and it's work in progress, and I'm already presenting it now because we are working on fields that we have very little experience with. So we would be thankful for suggestions and opinions. Are we too naive in some parts? What could be improved? Is this actually helpful, what we are doing? So Robin already mentioned in his talk that, yes, we have this nice framework of quantum causal models now, but it's not really useful yet. Like, we are not actually applying it to examples and finding, this teaches us something that we didn't know about these examples. And that's quite different for classical causal modeling, because this already gets applied in like all over science, except for physics, it seems. And actually, we want to change that in the long run. So to focus on something that's, how should I say, more practical, we are looking at definite causal orders, or in particular, quantum norms. And considering that my current group leader is Hans Briegel, it's probably not too surprising that we chose measurement-based quantum computation to look at. And now we want to look at some experiments where we are looking at sealed boxes and want to learn something about them. So Isaac and I searched all over the literature what could be helpful, and we found that if one knows nothing about the box, then also the quantum causality literature doesn't seem too helpful. So instead, we focus on some gray box scenarios that I will now take the time to define. After I've told you what measurement-based quantum computation actually is. So one considers some highly structured but highly entangled states called graph states. So the typical construction here would be one has some qubits that start out in the state plus, and then for each edge in the graph, one applies some CZ gate. So that's a way to implement these graph states. However, the hope is that these might also occur naturally as a ground state of a Hamiltonian, and that it might just be enough to take a many-body system, cool it down, and then one has the graph state without applying countless CZ gates. Then the computation is performed by just doing single qubit projective measurements. And in fact, one doesn't even need all of them. And usually one just considers the measurements that are taken from the XY plane of the qubit, which would be these states that I have written down here. And to show equivalence with the usual circuit models, there is a prescription for an elementary gate set, how to implement this as a sequence of measurements. But the problem is one has to assume that one always gets the plus outcome. And that's wrong with probability 1/2. So one can correct for these minus outcomes. And how one does the corrections induces a flow of corrections that is called flow, or in a more general variant, G-flow. And I will explain now the very simple basics of how this works. So if we get the minus outcome, this is actually equivalent to getting the plus outcome, but with an additional sigma z gate. And now the very important property about these highly symmetric graph states is that they have so-called stabilizers. Stabilizers are symmetry operators that don't change the graph state. And one picks out a certain node. This node gets a sigma x applied, Pauli x applied, and all the neighboring nodes get a Pauli z applied. And that's good because the mistake we made is also Pauli z. So we can erase this Pauli z that we didn't want if we complete a stabilizer. This means we apply the Pauli x and the Pauli z's such together that with the wrong Pauli z they form a stabilizer, and then the graph state is itself again, and everything's fine. This can be done in two ways. The one way is to directly apply the Pauli gates. But this would require the ability to do single qubit gates. Another thing that's more commonly done is that one adapts the measurement angles of future qubits. So I've written down here this equation now, and if alpha j is the angle that we wanted to apply originally, then we take all the corrections that from the previous qubits, and some of them will give us shifts by pi, and others will give us additional minus signs. And this is a prescription how one can also correct for wrong outcomes in previous qubits. And then the flow is just a particular recipe for how one does this completing with stabilizers. So where does one put the stabilizers to correct for wrong measurement outcomes? And now essentially this flow of corrections is a flow of information, and this is what we were interested in for modeling with a quantum causal model. So first of all, we are mainly interested here in the flow, so we are not modeling in detail the other parts of what's happening here. So first of all, this means that we are taking the graph state as an input, as an exogenous external input. And actually, this will make our causal model so-called semi-Markovian, because this graph state is entangled, it's correlated. And this would go against Reichenbach's principle, because we are not modeling where this correlation is coming from. then essentially the idea is that the agents themselves only perform the measurements. So they get a qubit from the process, which is the flow here, measure it, and then they output a classical result. And the process, on the other hand, takes the classical outcomes, takes a part of the graph state, then applies the corrections, and then sends the corrected graph state out to the corresponding agent. And we have this causal Markov decomposition that we've already seen in some talks, for example, Robin's talk. And then here on the right side of the arrow, I don't know whether you see the mouse pointer, there's a similar statement now with Scheu operators of channels. And we are listing the external graph state qubits, lambda j extra. So one might consider them to be parents, but we are listing them extra. And yes, these Scheus have to commute. So I'm not giving the details of here how this looks like, but essentially the Scheu operator describes a classically controlled channel where one reads the classical message and then applies the appropriate channel, which is actually a unitary channel, which just applies to Z and X gates. And if you really want to get to like the full quantum analog of a semi-Markovian classical structural causal model, you might want to say that, okay, everything should be unitary here. So this reading of the classical message is actually destructive. But you can undo that by sending the classical message to the causal future, and then this is a controlled unitary instead of a classically controlled channel. Okay, now the very helpful concept that we found is this comp min entropy here. And essentially, one considers this scenario here. We have a main agent that interacts with an eavesdropper in a controlled way. And the eavesdropper tries to learn a secret of the main agent. And to evaluate the success of the strategy, we are considering a referee. And the referee gets both the true value and the guessed value of the eavesdropper and decides how close they are. So there's this paper by Giulio Chiribella and Daniel Epler that defines the comp min entropy, and they are generalizing a paper by König, Renner, and Schaffner, where they are saying essentially if the guess and the true value are quantum, so some quantum states, then we would consider the perfect case to be, first of all, perfect correlation, and secondly, perfect phase matching. And because of that, the referee would then measure in this maximally entangled state. If the value to be learned is classical, then the best case would be perfect correlation. And in this case, one would measure with this incoherent projector here. And one important observation is that these are actually equivalent if the agent always outputs a classical value. So all what Chiribella and Epler have done in their paper does also apply to learning of classical variables. And then the min entropy is operationally defined as just the negative logarithm of the success probability, but optimized over all eavesdroppers. So there's also this other formula in their paper, which looks closer to the conditional min entropy that you might know for states. Typically, it's directly defined via such a formula. And very important is that in principle, this min entropy, which is essentially the best success probability, can be calculated as a semi-definite program like this. So we tried to put this into a computer, and it was just far too expensive. Like, I couldn't even define an identity matrix of this size in reasonable time. So we tried to simplify this because flow itself is essentially something classical. So it would be enough to just consider classical comps. But at least for my old computer, it seems to be barely out of reach to do this with classical comps. So the scenario that we found that fits into this is a particular protocol for blind quantum computation. So in blind quantum computation, one considers a client and a quantum server. And the client asks the quantum server to perform a quantum computation. However, the server is not supposed to learn what the quantum computation actually is. So at first, this seems impossible to do, like you're literally telling the server each single step. But this can be done, and also in classical computing, and there one uses something that is called homomorphic encryption. So yeah, essentially the idea is that one encrypts the computation, but in such a way that it can first of all still be performed and gives the actual results one wants to have. Now, this particular protocol by Atul, Mantri, and colleagues that we are considering here considers multiple rounds, and having multiple rounds is ideal for a quantum comp description. And the client tells the server to measure an angle, alpha j, which is alpha j prime, which is encrypted, and the server reports an outcome c-j prime, and this outcome might be a lie used to probe the client. So there are two basic security mechanisms that Mantri et al. Use. The first is to use one-time pads. So this is essentially the same formula as before for the corrected angles, but this time these RMs and RKs and RJs pop up here, and these are encrypted angles. And then the second security mechanism that made it into the title of the paper is called flow ambiguity, meaning that the server doesn't know the flow of corrections because the client implements the corrections by choosing the measurement angles. So in particular, there is no computational hardness assumption in the way of homomorphic encryption and one-way functions. And that's a problem because there are no-go theorems. For example, this one, Scott Aronson paper here, that says something like this should essentially be impossible. And we did find some sources that indeed say that there are problems, but we wanted to take our own spin on this. So, yeah. There will be essentially problems with multiple rounds, and in one of these papers it's said that the protocol is not composably secure, and where you can already see problems in the security analysis of the Mantri et al. Paper, because it uses quantities that are based on the von Neumann entropy. And these vector arrows essentially mean just from a single round. So we are taking the von Neumann entropy for a single round, which is a problem because the information theoretic derivation of the von Neumann entropy considers an asymptotic case of many IID repetitions. So it's much better to use single-shot entropies, like our min entropy, and some entropy accumulation theorems to investigate how multiple rounds perform in the security. Or what we are trying now is to use causality methods, so the quantum comp min entropy. And yes, as I already said, in principle, one could determine the best eavesdropping strategy with a semi-definite program. But this was too expensive for us. So we had to try to use some analytic properties of the min entropy to find things. And now for the single-shot case, we can prove that at least the one-time pads work. So it is partially secure. One cannot figure out the values of the one-time pads. But in the multi-shot case, Isaac found a small counterexample in which everything can be learned in the asymptotic case. And the reason for that is essentially that the one-time pads appear several times. So not just to encrypt the angle, but also to decrypt the classical outcomes. And this leads to correlations. And because we are always using the same underlying true quantum computation, and by that the same underlying measurement angles, we keep building up more and more consistency conditions. And at least for this one example, the consistency conditions are so restrictive that they only allow one possible value for the two angles, which can be found out that way. Yeah, so We also investigated some other causal discovery scenarios, for example, determining the measurement plane of an MVQC device if one doesn't already know it. And also, so far, even the most basic entropic properties of the comp mean entropy weren't even in the literature yet. So we also determined some of those. So how much time do I have left?
About 10 minutes and 20 questions.
Okay, then I will just rush through another project that I would really like to talk about. So this is about some quantum machine learning and another way how I want to take quantum causality more into practical matters. So supervised machine learning is essentially a sophisticated version of curve fitting that one encounters in lab courses. So one has some data points, like in the figure here, and then one wants to fit a parameterized function to it, which might be a linear curve, but one doesn't know its parameters yet. And usually in supervised machine learning nowadays, this parameterized ansatz is an artificial neural network. But most of quantum machine learning research nowadays considers a so-called variational quantum computation. So one has a fixed ansatz, which, for example, might be many layers of the form in this picture, but there are some free parameters that one can tune, which would here be the angles theta. And then the goal is to choose these parameters, for example, with a gradient descent, such that the classical input-output statistics perfectly, or as well as possible, reproduces some training data. So essentially, the red curve in the figure now is the classical input-output statistics of our variational quantum circuit. And recently, by the group around Giulio Chiribella, it was discovered that the quantum switch that we already encountered several times has a very important property, namely that if one inputs some maximally noisy channels, then they are capable of transmitting information again. But it's not too nice, because to get this effect, one has to sacrifice one perfectly clean transmission of the control qubit. So this activation doesn't come from nothing. One does have to make a sacrifice. So I was interested then, okay, when is this worth it? Well, it might be worth it if we replace the simple channels with some complex variational quantum computers. So but then the quantum switch protocol itself sadly doesn't work, because it's known that the quantum switch does not depend on the Krauss operator decomposition, so it can't see the difference between a simple maximal noise channel and another one where there's some unitary computation hidden inside. But this changes then in this other scheme that was considered in this paper by Alistair Abbott, Julian Wex et al., where one considers just channels in parallel. And now here the control qubit decides where does the input go, to which channel does it go. This means the other channel that was not chosen gets the vacuum. And that's very important, because now we need to construct a vacuum extension, and this will actually bring in a dependence on the Krauss operators. So I didn't like too much the construction in their original paper, because it didn't have the vacuum. So I did the calculation again with a unitary dilation. And I'm actually defining the Krauss operators now from this unitary dilation. So this is how the Krauss operators now come in. And then I make some physical assumptions. So the environment should be pure, the vacuum should have a trivial evolution, and I demand that the environment doesn't interact with the vacuum. Now, furthermore, one chooses the control qubit to be, again, in this plus state, and one measures also the control qubit in the plus-minus spaces. And then the output density matrix for the different results, if one subtracts this, leads to this form here. So psi is the input, and these matrices are some weighted superposition or weighted sum of the noisy Krauss operators, and the coefficients depend on the environment. Yes. And then I looked at an example, which is like, again, layers of a quantum machine learning algorithm of a variational quantum circuit, but with some noise inserted. And the noise I chose to be maximal noise channels on each qubit using these Krauss operators here, so standard Pauli maximal noise. And then one can repeat this calculation, but now one has a factorizing environment, one for each qubit. And then again, one finds that essentially the maximal noise channels are replaced by these matrices R, the same as up here. And this is now a 2x2 matrix, so we can actually calculate its properties. And what one finds is that it is invertible for almost all environment states. So because it's invertible unless its determinant is 0. So being non-invertible would be highly fine-tuned. So in other words, we have taken maximally noisy variational quantum circuits that have absolutely no parameter dependence anymore. So they cannot be used to fit any function because they have no parameter dependence. But this noise mitigation scheme, we placed the parameter dependence we placed the noise with an invertible matrix R. And because it's invertible, we do get back our parameter dependence. It's almost like replacing the noise with a fixed unitary, except that here it's not a unitary, but any invertible matrix. And yes, I would like to investigate this in far more detail. So far, I've only this one example in detail. So, yes, I think this is a good point for Andrew and for a question. We should have about 5 minutes left.
Let's thank Marius. Thank you for a very nice talk. Do we have questions?
Hello? Yeah. Hi, Marius. Thanks for the very complete talk. I had a question about your second part, the one about the no-go theorem for parallel composition. So if I'm correct, you motivated it partly by saying that one would like to have a Shannon theory of process matrices.
Yeah, like it doesn't even have to be a full Shannon theory, but in quantum information, we like to do lots of tensor products, and we like to actually have an advantage provided by parallel implementations. And denoising by inputting one large entangled state and doing one large measurement on parallel implementations of a channel would be an example where this matters.
Okay, so you might have heard that some people have designed parallel compositions for process matrices, which basically correspond to just typing the parallel composition of the process matrices as only admitting non-signaling channels between the different ports. It's in a paper by Kissinger and Wijlen, and I think the idea is from Perinotti. So I was wondering if...
I need to see the details of that to say more. So essentially, the project began by looking at some particular conjectures for how these parallel compositions might look like. But essentially, all that we found was either incompatible with this reduction to the tensor product postulate. So this is actually the breakthrough, and I think it was Philippe's idea.
Yeah, I think it's going to be incompatible with...
Or it requires post-selection.
No, it's going to be incompatible with the third postulate, but one might argue it's natural, in fact. But my question was, do you... I mean, yeah, I don't know if you're familiar with it, but my question was, if you were familiar with it, do you think this could lead to a well-defined Shannon theory for process matrices?
Like I would have to see them in detail.
Okay,
I remember one rather old paper, I think just by Perinotti alone, that in a very abstract way defined a tensor product, We had problems with that, but this was too many years ago. I don't remember what the problems with those definitions are.
Okay, thank you.
Hello. Yeah, thanks for the interesting talk. So my question is also related to this no-go theorem for composition. Here, right in front of you. So actually it's related to sort of this physical interpretation of this theorem, and also it's a bit of a question and a comment. So I find it useful to distinguish the information theoretic and space-time notion of causality, right? And I guess if you think of this physically as, because in the particular example, the two processes you're composing are precisely definite causal order processes with two different directions, and one could do this on a tabletop in principle, each of those processes separately. And we would not imagine there would be some problem with composing. But if you kind of try to follow what's really happening, if Alice in one process sends something signals to Bob, and then Bob signals to Alice, and if we sort of really look at in space-time what's happening, Alice will receive something twice, or she would be acting twice. And in the first case, she's sending something, and later. And then the paradox looks sort of, in a sense that it's not that there's an outcome that's both 0 and 1, but it's the outcome at time 1, which is 0, and an outcome at time 2, that's 1, for instance.
Yes.
Would that...
So it would be kind of like an unraveling, like essentially saying we assign some kind of proper time on this loop, and then each time we meet the sigma x, the proper time has increased, and then it's unraveled.
So would you think of this theorem as kind of being cautioning you about, or like being a cautionary tale about having to take this kind of both these pictures into account?
Yes. So the difference here would be that implicitly, by the fact that we even write down process matrices that looks like that, we are implicitly assuming that the operations of the agents only happen once, and that this causal unraveling cannot happen. And I think there's also some difference to what Roger presented about your work on causal loops in space-time. So my impression was that it was in the title that they are fine-tuned, in the sense that a lot of this relied on the fact that one had a maximally mixed state that washed out all differences. And I think if one used a different state that had a bias into one direction, then the consistency might disappear. But
you're exactly right. Yeah,
okay.
Indeed, because that is also in not the split node causal model picture.
Yeah.
So doesn't have an interpretation as a process operator. And if you sort of try to interpret it as a process operator, indeed, as you say, you'll find some interventions for which it's not consistent.
Yes, and I think that's very important here, because we are working in the process matrix picture. So we allow the agents to do all operations here. So the causal loop is not always a problem, right? Because if this Pauli X wasn't here, then everything would look consistent. Or if Alice just traced out the input and did nothing with it, that would also break the causal loop. So the logical inconsistencies here one gets are only for some operations of the agents.
Yeah, and the distinction is also whether you assign a single space-time location to each agent, or you're thinking of them as you're allowing them to act multiple times in the space-time. Indeed. So thanks. Yeah.
Questions?
Pass this one. This seems to be working at the moment.
Yeah, it's more a follow-up comment on when you think about realizable switches, optical switches, for example. And obviously you can put one on the top of each other, I mean, in space. But then if you define here an action of map to be always when you have two particles in your lab, then if you have two switches on the top of each other, then you have all kinds of combinations, like from the first switch it comes...
So you mean with the particle number, right?
With the particle number.
So in the optical implementations, for example, by Julia here, essentially the particles enter the labs at different times.
Exactly.
And if one wants the particles to be in the extended labs at the same time, one would have to do some post-selection.
Yeah, you basically post-select the case such that you have a valid process matrix, namely both particles go through Alice or both particles goes to Bob.
Yes. But yes, we are explicitly not considering the case of post-selection here. So just like the usual tensor product, we want it to always succeed.
Questions? More questions? Do we have online questions?
Can I?
No. Okay. Otherwise, thank you again, Marius.